Hello and welcome to this new video in which we are going to talk about statistics. First of all, we'll present variables in statistics, and after that, we'll deductive statistics. Finally, we'll introduce hypothesis testing. Important to go deeper into the analysis. If you discover our channel for the very first time, don't hesitate to activate the notification bell so you don't miss any of the next videos. A like and sharing this video will also make us happy and allow many other people to discover it. Let's start with basics of statistics. Statistics is the science of collection, presentation, analysis, and reasonable interpretation of data. It presents a rigorous scientific method for gaining insight into data. For example, suppose we measure the weight of 100 patients in a study. With so many measurements, simply looking at the data fails to provide an informative account. However, statistics can give an instant overall picture of data based on graphical presentation or numerical summarization irrespective to the number of data points. Besides data summarization, another important task of statistics is to make inference and predict relations of variables. A taxonomy of statistics. Statistics has two main branches: descriptive and inferential. In descriptive methods we have univariate, bivariate and multivariate statistics. As far as univariate statistics is concerned, what can be done is shape, center, spread and relative position. Bivariate statistics look at things like correlation and regression for prediction purposes. Lastly, we have multiple regression in multivariate statistics. Statistical description of data. A variable is a characteristic that can be measured and that can assume different values. Height, age, income, province or country of birth, grades obtained at school and type of housing are all examples of variables. Types of variables. Variables may be classified into two main categories: categorical and numeric. Each category is then classified in two subcategories: nominal or ordinal for categorical variables, discrete or continuous for numeric variables. These types are briefly outlined in this video. Categorical variables. A categorical variable, also called qualitative variable, refers to a characteristic that can't be quantifiable. Categorical variables can be either nominal or ordinal. Nominal variables. A nominal variable is one that describes a name, label or category without natural order. Sex and type of dwelling are examples of nominal variables. In Table 1, the variable mode of transportation for travel to work is also nominal. Ordinal variables. An ordinal variable is a variable whose values are defined by an order relation between the different categories. In Table 2, the variable behavior is ordinal because the category excellent is better than the category very good, which is better than a category good, etc. There is some natural ordering, but it is limited since we do not know by how much excellent behavior is better than very good behavior. It is important to note that even if categorical variables are not quantifiable, they can appear as numbers in a data set. Correspondence between these numbers and the categories is established during data coding. To be able to identify the type of variable, it is important to have access to the metadata, the data about the data, that should include the code set used for each categorical variable. For instance, categories used in Table 2 could appear as a number from 1 to 5 to 1 for very bad, 2 for bad, 3 for good, 4 for very good, and 5 for excellent. Numeric variables. A numeric variable, also called quantitative variable, is a quantifiable characteristic whose values are numbers, except numbers which are codes standing up for categories. Numeric variables may be either continuous or discrete. Continuous variables. Variable is said to be continuous if it can assume an infinite number of real values within a given interval. For instance, consider the height of a student. The height can't take any values. It can't be negative and it can't be higher than 3 meters. But between 0 and 3, the number of possible values is theoretically infinite. A student may be 1.632174875 meters tall. In practice, the methods used and the accuracy of the measurement instrument will restrict the precision of the variable. The reported height would be rounded to the nearest centimeter, so it would be 1.63 meters. The age is another example of a continuous variable that is typically rounded down. Discrete variables, as opposed to a continuous variable. A discrete variable can assume only a finite number of real values within a given interval. An example of a discrete variable would be the score given by a judge to a gymnast in competition. The range is 0 to 10 and the score is always given to one decimal, e.g. a score of 8.5. You can enumerate all possible values, 0, 0.1, 0.2, and see that the number of possible values is finite. It is 101. Another example of a discrete variable is the number of people in a household for a household of size 20 or less. The number of possible values is 20. Because it's not possible for a household to include a number of people that would be a fraction of an integer like 2.27 for instance. In summary, we have two types of variables. 1. Categorical variables which is divided in nominal and ordinal. 2. Numeric variables which is divided in continuous and discrete. Descriptive statistics. Statistics describes a numeric set of data by a center, variability, shape. Statistics describes a categorical set of data by frequency, percentage or proportion of each category. Here are some definitions. Variable. Any characteristic of an individual or entity. A variable can take different values for different individuals. Variables can be categorical or quantitative. Nominal. Categorical variables with no inherent order or ranking sequence such as names or classes, e.g., gender. Value may be a numerical, but without numerical value, e.g., I, 2, 3. The only operation that can be applied to nominal variables is enumeration. Ordinal. Variables with an inherent rank or order, e.g. mild, moderate, severe, can be compared for equality. Or greater or less, but not how much greater or less. Interval. Values of the variable are ordered as in ordinal, and additionally, differences between values are meaningful. However, the scale is not absolutely anchored. Calendar dates and temperatures on the Fahrenheit scale are examples. Addition and subtraction, but not multiplication and division are meaningful operations. Ratio. Variables with all properties of interval plus an absolute, non-arbitrary 0 point, e.g. age, weight, temperature, Kelvin. Addition, subtraction, multiplication, and division are all meaningful operations. Distribution of a variable tells us what values the variable takes and how often it takes these values. Unimodal, having a single peak bimodal, having two distinct peaks symmetric, left and right half are mirror images. Frequency distribution. Consider a data set of 26 children of ages 1 to 6 years. Then the frequency distribution of variable age can be tabulated as follows. Cumulative frequency. Cumulative frequency of data that we showed you earlier on the tables. Data presentation. There are two types of statistical presentation of data, graphical and numerical. Graphical presentation. We look for the overall pattern and for striking deviations from that pattern. Overall pattern usually described by shape, center, and spread of the data. An individual value that falls outside the overall pattern is called an outlier. Bar diagram and pie charts are used for categorical variables. Histogram. Stem and leaf and box plot are used for numerical variable. Data presentation categorical variable. Bar diagram. Lists the categories and presents the percent or count of individuals who fall in each category. Pie chart. Lists the categories and presents the percent or count of individuals who fall in each category. Numerical variable. Histogram. Overall pattern can be described by its shape, center, and spread. The following age distribution is right skewed. The center lies between 80 to 100. No outliers. Box plot describes the 5-number summary. Numerical presentation. A fundamental concept in summary statistics is that of a central value for a set of observations and the extent to which the central value characterizes the whole set of data. Measures of central value such as the mean or median must be coupled with measures of data dispersion, e.g., average distance from the mean, to indicate how well the central value characterizes the data as a whole. To understand how well a central value characterizes a set of observations, let us consider the following two sets of data, 30, 50, 70b, 40, 50, 60. The mean of both two data sets is 50. But the distance of the observations from the mean in dataset A is larger than in the dataset B. Thus, the mean of dataset B is a better representation of the dataset than is the case for set A. Commonly used methods are mean, median, mode, geometric mean, etc. Mean. Summing up all the observation and dividing by number of observations. Mean of 20, 30. 40 is 20 plus 30 plus 40, divided by 3, which is equals 30. Let x1, x2, xn are n observation of a variable x. Then the mean of the variable is x1 plus x2 plus xn divided by n, median. The middle value in an ordered sequence of observations. That is, to find the median we need to order the dataset and then find the middle value. In case of an even number of observations, the average of the two middlemost values is the median. For example, to find the median of 9, 3, 6, 7, 5, we first sort the data giving 3, 5, 6, 7, 9. Then choose the middle value 6. If the number of observations is even, e.g., 9, 3, 6, 7, 5, 2, then the median is the average of the two middle values from the sorted sequence, in this case, 5 plus 6, 2 equals 5.5. Mode. The value that is observed most frequently. The mode is undefined for sequences in which no observation is repeated. When to use mean or median? The median is less sensitive to outliers, extreme scores, than the mean and thus a better measure than the mean for highly skewed distributions, e.g. family income. For example, mean of 20, 30, 40. And 990 is 20 plus 30 plus 40 plus 990, divided by 4, which is equals 270. The median of these four observations is 30 plus 40, divided by 2, which is equals 35. Here 3 observations out of 4 lie between 20 to 40. So, the mean 270 really fails to give a realistic picture of the major part of the data. It is influenced by extreme value 990. Methods of variability measurement. Variability, or dispersion, measures the amount of scatter in a dataset. Commonly used methods: range, variance, standard deviation, interquartile range. Coefficient of variation, etc. Range, the difference between the largest and the smallest observations. The range of 10, 5, 2, 100 is 100 to 2 equals 98. It's a crude measure of variability. Methods of variability measurement. Variance. The variance of a set of observations is the average of the squares of the deviations of the observations from their mean. Variance of 5, 7, 3. Mean is 5 plus 7 plus 3, divided by 3, which is equals 5, and the variance is 5 to 5, square plus 3 to 5, square plus 7 to 5, square divided by 3 to 1, which is equals 4. Standard deviation, square root of the variance. The standard deviation of the example is 2. Quartiles. Data can be divided into 4 regions that cover the total range of observed values. Cut points for these regions are known as quartiles. In notations, quartiles of a data is the n plus 1 divided by 4 qth observation of the data, where q is the desired quartile and n is the number of observations of data. The first quartile, q1, is the first 25% of the data. The second quartile, q2, is between the 25th and 50th percentage points in the data. The upper bound of q2 is the median. The third quartile, q3, is the 25% of the data lying between the median and the 75% cut point in the data. Q1 is the median of the first half of the ordered observations and Q3 is the median of the second half of the ordered observations. In the following example, Q1 equals 15 plus 1 divided by 4 equals 4th observation of the data. The 4th observation is 11. So Q1 is of this data is 11. An example with 15 numbers 3, 6, 7, 1, 1, 1, 3, 2, 2, 3, 0, 4, 0, 4, 4, 5, 0, 5, 2, 6, 1, 6, 8, 8, 0, 9, 4. The first quartile is Q1 equals 11. The second quartile is Q2 equals 40. This is also the median. The third quartile is Q3 equals 61. Interquartile range. Difference between Q3 and Q1. Interquartile range of the previous example is 61 to 40 equals 21. The middle half of the ordered data lie between 40 and 61. Decils and percentiles. Decils. If data is ordered and divided into 10 parts, then cut points are called decils. Percentiles. If data is ordered and divided into 100 parts, then cut points are called percentiles. 25th percentile is the Q1, 50th percentile is the median, Q2, and the 75th percentile of the data is Q3. In notation, percentiles of a data is the n plus 1 divided by 1 OOPTH observation of the data, where p is the desired percentile and n is the number of observations of data. Coefficient of variation, the standard deviation of data divided by its mean. It is usually expressed in percent. The coefficient of variation is the ratio of standard deviation and mean time 100 and is measured in percentage. 5-number summary. The 5-number summary of a distribution consists of the smallest, minimum, observation, the first quartile, Q1, the median, Q2, the third quartile, and the largest, maximum, observation written in order from smallest to largest. Box plot. A box plot is a graph of the 5-number summary. The central box spans the quartiles. A line within the box marks the median. Lines extending above and below the box mark the smallest and the largest observations, i.e., the range. Outlying samples may be additionally plotted outside the range. We like to think of statistical hypothesis testing as the data analysis stage of a comparative experiment in which the researcher is interested, for example, in comparing the mean of a population to a specified value, e.g. mean pull strength. The general goal of a hypothesis test is to rule out chance, sampling error, as a plausible explanation for the results from a research study. Hypothesis testing is a technique to help determine whether a specific treatment has an effect on the individuals in a population. The hypothesis test is used to evaluate the results from a research study in which 1. A sample is selected from the population. 2. The treatment is administered to the sample. 3. After treatment, the individuals in the sample are measured. In this graph, weaken a known population before treatment with a mean of 80 and standard deviation of 20. After a treatment, we have an unknown population with supposed same variance and undifferent standard deviation. If the individuals in the sample are noticeably different from the individuals in the original population, we have evidence that the treatment has an effect. However, it is also possible that the difference between the sample and the population is simply sampling error. The purpose of the hypothesis test is to decide between two explanations. 1. The difference between the sample and the population can be explained by sampling error. There does not appear to be a treatment effect. 2. The difference between the sample and the population is too large to be explained by sampling error. There does appear to be a treatment effect. The null hypothesis, the alpha level, the critical region, and the test statistic. The following 4 steps outline the process of hypothesis testing and introduce some of the new terminology. Step 1. State the hypotheses and select an alpha level. The null hypothesis, H0, always states that the treatment has no effect, no change, no difference. According to the null hypothesis, the population mean after treatment is the same as it was before treatment. The alpha level establishes a criterion, or cutoff for making a decision about the null hypothesis. The alpha level also determines the risk of a type 1 error. Step 2. Locate the critical region. The critical region consists of outcomes that are very unlikely to occur if the null hypothesis is true. That is, the critical region is defined by sample means that are almost impossible to obtain if the treatment has no effect. The phrase almost impossible means that these samples have a probability, p, that is less than the alpha level. Step 3. Compute the test statistic. The test statistic, in this chapter a z-score, forms a ratio comparing the obtained difference between the sample mean and the hypothesized population mean versus the amount of difference we would expect without any treatment effect, the standard error. Step 4. A large value for the test statistic shows that the obtained mean difference is more than would be expected if there is no treatment effect. If it is large enough to be in the critical region, We conclude that the difference is significant or that the treatment has a significant effect. In this case, we reject the null hypothesis. If the mean difference is relatively small, then the test statistic will have a low value. In this case, we conclude that the evidence from the sample is not sufficient, and the decision is failed to reject the null hypothesis. Errors in hypothesis tests. Just because the sample mean, following treatment, is different from the original population mean does not necessarily indicate that the treatment has caused a change. You should recall that there usually is some discrepancy between a sample mean and the population mean simply as a result of sampling error. Because the hypothesis test relies on sample data, and because sample data are not completely reliable, there is always the risk that misleading data will cause the hypothesis test to reach a wrong conclusion. Two types of error are possible. Type 1 error. A type 1 error occurs when the sample data appear to show a treatment effect when, in fact, there is none. In this case, the researcher will reject the null hypothesis and falsely conclude that the treatment has an effect. Type 1 errors are caused by unusual, unrepresentative samples. Just by chance, the researcher selects an extreme sample with the result that the sample falls in the critical region even though the treatment has no effect. The hypothesis test is structured so that type 1 errors are very unlikely. Specifically, the probability of a type 1 error is equal to the alpha level. Type 2 errors. A type 2 error occurs when the sample does not appear to have been affected by the treatment when, in fact, the treatment does have an effect. In this case, the researcher will fail to reject the null hypothesis and falsely conclude that the treatment does not have an effect. Type 2 errors are commonly the result of a very small treatment effect. Although the treatment does have an effect, it is not large enough to show up in the research study. Directional tests. When a research study predicts a specific direction for the treatment effect, increase or decrease, it is possible to incorporate the directional prediction into the hypothesis test. The result is called a directional test or a one-tailed test. A directional test includes the directional prediction in the statement of the hypotheses and in the location of the critical region. For example, if the original population has a mean of 80 and the treatment is predicted to increase the scores, then the null hypothesis would state that after treatment, H0 mean is less than 80, there is no increase in this case. The entire critical region would be located in the right-hand tail of the distribution because large values for M would demonstrate that there is an increase and would tend to reject the null hypothesis. Measuring effect size. A hypothesis test evaluates the statistical significance of the results from a research study. That is, the test determines whether or not it is likely that the obtained sample mean occurred without any contribution from a treatment effect. The hypothesis test is influenced not only by the size of the treatment effect but also by the size of the sample. Thus, even a very small effect can be significant if it is observed in a very large sample. Because a significant effect does not necessarily mean a large effect, it is recommended that the hypothesis test be accompanied by a measure of the effect size. We use Cohen equals SD as a standardized measure of effect size. Much like a Z-score, Cohen equals SD measures the size of the mean difference in terms of the standard deviation. Power of a hypothesis test. The power of a hypothesis test is defined as the probability that the test will reject the null hypothesis when the treatment does have an effect. The power of a test depends on a variety of factors including the size of the treatment effect and the size of the sample. That's it for this video and we hope you find it useful. And if you haven't done so yet, don't hesitate to subscribe and activate the notification bell so you don't miss any of our upcoming videos. A like and sharing of this video will also make us happy and allow many other people to discover it while knowing that all the efforts we make allow you to improve on a daily basis on statistical models applied to the social sciences. On this we say see you very soon for a new video.